All right. Hopefully it goes better this time. Um, so, where were we? Oh, yes. Dev.to Frontend Challenge. Okay, so we're going to create a project here with this markup, and we're going to put together a really basic static file website set of pages, basically. You could call it an app, but that's, you know, the word app can mean a lot. And we're going to use Three.js, one of my favorite libraries, to sort of take this markup and spin it up into like a 3D view of the solar system. So let's see how long it takes for us to do that. Uh, so GitHub, repository, new. This is 20 of 2, random, Dev.to front end challenge. Boink. Let's clone that. Voila. Enter repository. Yes, thank you very much. There is a secondary motive here, of course, which is I need to get better at live coding and live. I deliberately am trying to make this not a production, by the way, just overall for channel content. But in this case, I do need to be better about like the math problems yesterday were just atrocious when I tried to walk through static problems like live coding and live math. I got to get better at this. So from the command line here, let's go ahead and let's see, yarn create vite template vanilla here. Yarn install. Well, let's see, npm, yes, make sure I'm getting the right reference for 3. JavaScript 3, yep, it's just 3, it's not Three.js. Okay, so yarn add 3. Boinky, boinky, boink. All right, and yarn run dev. So let's create a new here. Make sure Vite did what we expected it to. Voila, okay. Let's see. Boink. Let's get dirty. Let's start tearing stuff out, right? So let's talk about the overall. This actually has some interesting applications for some other things as well. But let's talk about the overall structure of this application. For a 3D application, especially an interactive 3D application, there's effectively, if you do like game engine design or game development, there's typically 3 loops or activities that are going on at any given point in time. And if you have something that's doing all instructions in serial, that means that every iteration of the game loop is broken up into 3 segments. Nowadays, you can of course optimize a lot of this by breaking those apart and running them concurrently with the right memory access models. But there's 3 basic activities that are taking place within the main loop here. There's some sort of user. I'd say IO, but it's usually just O, right? Or usually just I. Input polling or input events. There's, of course, rendering. The render calls themselves. And there's some sort of like actual internal logic or update, right? And then you could wonder like, well, what about, networking interactions, et cetera. Basically, those you could treat those as input events of some kind. There's some sort of asynchronous event driven, there's an update packet or what have you that comes in, and then that goes into a queue or a stack, and you need to apply some sort of update to the state. So there is some fundamental underlying state, right? For the purposes of Three.js, we'll use that, we'll borrow that very simple but useful model. And only for, updating does that state mutate. So there's some intermediate queue of events or what have you And maybe this, if you're using an ECS, this might be like a set of component tables, right? And then you need to worry about how those are managed or updated over time. We won't go quite into that much complexity. Just keep in mind that sort of the event loop logic for this application decomposes into basically 3 loops or subloops where the user input events are triggered. In this case, for a web app, I'm just by DOM, right? By the actual browser, and then we'll have specific events that we listen to and manage with like a observable or a pub/sub interface. The rendering itself is mostly baked into Three.js. We just worry about how the scene graph is set up, constructed, what sort of controls might be applied, and then the update itself is where most of our custom logic will go to move the planets around, for example. So we have this. Let's first see if we can get sort of the classic basic Three.js demo going. So here is the Vite content. Make sure I am not making a fool of myself. There we go. All right. So we're going to strip out a lot of stuff here. We don't need you. We don't need you. Some sort of style sheet. Let's call it index CSS. Type text CSS. Let's see. Width. We are going for sort of a fullish screen or full window, right? 3D context here. So we'll say no overflow. That's our body element here. And then, last but not least, tie in our ES6 module. We will right here. Of course, that assumes that we don't fat finger anything. How many things do you think we can type out today? Many. So on window load. Call me old school, but use good names for your event listeners, etc. And now we can start pulling out things, right? So we don't need you. We don't need you. We don't need you. We don't need you. It's probably worth putting together an actual Vite template for 3 at some point. I should do that. And so now we have absolutely nothing. Isn't it wonderful? Isn't it glorious? Of course, we can go in and say, hey, yep, Windows loaded. Yay for hot module replacement. So let's go ahead and go here into our entry point. A lot of this is not particularly necessary, but we're going to stick as close as possible to the traditional. Oh, you know what I should do? Mark up. And we'll put this here, right? Boink, boink, boink. All right, so there's our markup that will be person presenting. Every 3 so 3 has a very specific graphics pipeline here, which is there exists some renderer. One of the properties for that renderer is its target. So this can be passed explicitly, or it will create one on its own. So this is like a canvas element, right? There is also some sort of scene, and there is some sort of camera. So the rendering call for 3 is just renderer.render scene camera. It's a simple model, but a beautiful one, in particular because you can break down this scene into, of course, this should surprise no one, like a tree of nodes, right? Each with its own transform. Um, those nodes, and the scene is just like the top level node in what we call a scene graph. And so each of those scene graph nodes, um, 3.mesh, if I remember correctly, there's technically like a 3D object that purely focuses on transformation, but if we look at 3mesh, what we'll see is it has a transform, it has some sort of geometry property. So this is basically your vertex buffer, right? All of your vertex properties. And it has a material, and that's basically your shader. So 3 itself, given this call, that render.render call, will go in and traverse the scene graph and in turn basically build up the rendering calls and execute them on its own with the with support for swapping in different specific custom shader programs if you need them. And then anything like meshes or other things can be loaded from external data or defined using predefined geometries, and you can access those buffer attributes of the usual graphics programming techniques. But for now, let's just focus on getting the basic going here. If you use 3, you know, there's absolutely no surprises here. I've been saying that a lot, haven't I? I need a better way to juggle multiple screens here. Scene. So in this case, we're going to use a predefined geometry with a specific constructor. Just to get things going here. Same thing. Normal material basically has the colors defined by the unit coordinates of the normal at any given vertex. And we can go into, and probably will, more graphics programming at some point. You construct a new mesh from the geometry and the material, so the vertex data and the shader program. Then you can add that to a given scene graph node. In this case, we'll say that's at the top node. And now we can define our renderer. We will use a WebGL renderer here. There is web GPU support that they are building out, and I'm really excited to see what that can do. I haven't had a chance to mess with it much myself yet. Notice we didn't pass a DOM element, so it creates a canvas on its own. And then we will add that. The less we have to mess directly with DOM, the better. Okay, so now you'll notice we had a call here. This is the animation loop. We will define that as a separate event. Takes time as a parameter, and we'll spin the cube around. And again, this is literally just a super basic, you know, hello world of 3JS. At one point, you had to set like request animation calls or request draw calls manually. I'm guessing in the newer versions it does that for you. So let's see if that worked. It did not work. Let's see what went wrong. Mesh, add mesh. Ah, yes. Mesh does not exist within that context. So here's what we're going to do. A couple of ways we could go about this. So fundamentally, the problem here is the fact that within a web page, the global context is the window, right? That is the singleton in which everything, all other of symbols are evaluated. So we need some sort of unifying context to define what the state of the application is here. So we already talked about this, right? So at the top level, we have a render and a scene and a camera. So let's use that model as our global singleton here. What are our scene references? Go. Camera references. And our rendering call. Render. Okay, now we're ready for this. App render, app scene, and camera. Okay. What went wrong this time? App.mesh is undefined. Oh, that's right. Will you look at that? Obviously, a lot of work to do here, right? So let's look at the canvas. We know that's not right. That should be basically lined up with our body. So our body has some margin and padding. We're going to want to set that to 0. There we go. And then last but not least, we're going to add something called orbit controls. This is basically the main way that the user will interact with, in this case, camera controls, is through mouse clicking and dragging, right? So this is fortunately built into 3JS, but not necessarily the global export. So it's grab it from the add-ons here. Voila. And then there are a couple of things we need to do. We need to instantiate it. And then we need to put it in the update. Now, as you probably might guess, that will also need to be in the global context. That's not part of the pipeline. And therefore, now we can update it from our animation loop. All right, so now, look at that. We can drag around, we can zoom. Hey, think of what I'm thinking. Just so we have an understanding, we're going to be working with some coordinates in a coordinate system, so we will want to go ahead and add in 3JS what's called the axis helper. That is built into the global export. When we construct our scene here, we add sort of this this cube to the scene, right? But we're also going to add this axis helper. We'll say it has units of 3 along each axis. And look at that, we got some axes here. Let's make this a unit cube just so we have a better scale. And let's start our camera out at Z10. Look at that. You will notice the depth buffers, or the near and far clipping, actually, rather, starting to cause some issues here. So let's go 1E minus 3 to 1E 3,000. There you go. Isn't that beautiful? So far, so good. Okay, so now let's go ahead and give this a commit. We're actually ready to start getting crazy here. Ready for crazy. Don't you love just not so conventional commit messages? But obviously this is enough for us to get started, right? So let's now, what do we want to do next? Let's pull up what the solar system should look like. In particular, we need to start worrying about things like, as we saw with the other example, these coordinates. So the farthest object out here from our markup is possibly Pluto, Kuiper Belt, including Pluto. All right, so we'll use, if I can remember the difference between the Kuiper Belt and the Oort cloud. Let's use the orbital diameter of Pluto here as our outer limit. That is, we'll stick with base SI. 7.3 billion kilometers, that's a lot. But here's the beautiful thing. This is all floating point arithmetic under the hood, right? That's the only thing the GPU cares about. So what really matters is the precision that can be represented between objects that the GPU has to take into account in the depth buffer. So these numbers can be as big and as small as we want them to be, so long as there is sufficient precision relative to the depth that will be considered in the depth buffer to be able to tell the difference between, Earth is in front of Mars or vice versa, depending on what your perspective is. So we can go ahead and set this out as far as we want. I said 3 billion or 7.3 billion kilometers. Let's just round that. Let's round that up, right? So 6 million E9 billion, so 8 E9. I said base SI, should we use kilometers? Let's just use kilometers. And then if we want, 83 should be fine, should be enough. 6 orders of magnitude, I can't remember exactly what that translates to. Of course, now we did scale everything up too. So a couple of things we're going to do here. First, we're going to replace this box at the center with a sphere. This is a slightly different constructor. The radius is going to be, stop me if this value sounds familiar. It's roughly 7. Where we go? 7E8 meters, so that's 5 kilometers. And then we'll give it 32 sections. We're going to use a different material here. I really do want to do a graphics programming tutorial at some point so we can talk about materials and shaders and other things. We're going to use a mesh long material. It has nice parameterization, not particularly crazy. If I can remember what the constructor is. And it's just going to live at the center. The other thing that needs to change here is our axes. We'll give this 26 so we can see them outwards. And our initial position, 1E7 in Z. We do need a light. That can be too much at this point. Should we? Basic material. Let's do a mesh basic material instead for now. Voila. Look at that. And we have a sun. There is the sun. And the dimensions are realistic, right? So at this point, I mentioned ECS earlier. The complexity constant with ECS to implement is a little high. Well, also, we already have a scene graph model built into the 3JS interface. So we're just going to reuse and extend the existing models in 3JS, and we're going to say, let's see, what do we need to customize? We're We need a reference to the mesh. So I'm thinking about how we model these objects that we're going to present. We need a reference to the mesh. The position is going to be updated as they fly around the sun, right? And we need, honestly, that's about it, isn't it? There may be some other unique parameters for dimensions, etc. Let's hard code those for now. It'll probably be pretty obvious by the time we get partway through what the reusable approach will be. So let's say, camera instantiation, scene instantiation, render instantiation, controls instantiation. And you know, we can probably put this here. Let's make sure nothing died. Okay, we're good. All right, so let's continue instantiating our scene here. Let's consider the planet Mercury, right? So Mercury is, I've been going back and forth in my head about whether we'd like actually walk through the planetary ephemerides or not. We probably won't. I think circular orbits for now are probably fine. We can update that if we need to, but we will need a, angular velocity of some kind to move it around. Let's say, here we are. What kind of parameters do we really care about? So for instantiating the sphere for each of these elements, 32 by 32 grid points on the sphere is fine. The radius will change. The initial position, which we don't set, is going to change. So radius, initial position, the angular velocity as it orbits about is going to change. The color is going to change. What else do we want to change? That's probably good enough for now, right? So now we have some basic idea of what the model here is, and we could pull out a class if we wanted to, but we're just going to reuse the mesh and say, build a planet. Oh, yeah, I said initial position. So radius, we'll come up with units for those later. Given Mercury, we'll say, let's say, planet constructor is, so this is the sun, which is not a planet. Construct sun manually. We could probably change that at some point, but for now it's fine. Scene has axes. Okay, so app scene add build planet. So the Mercury's radius is it's a 2.4 E3 kilometers. That's a small ass planet. Let's see, what else do we say? The initial position, we'll use three's linear algebra types here. It's semi-major axis of its orbit is 57.91 E6 million kilometers. We will just start it out on the x-axis for now. We'll worry about propagation later. It's a angular velocity. So this is where we might want to pull out some math here. I'm just using, by the way, this may not surprise you, the Wikipedia page here. Lots of useful stats. Nothing crazy. But let's do a tiny bit of math here. So for a given orbit, one of the properties that Wikipedia will tell you is something called the orbital period. We will call that t as a variable. And in this case, let's say we know that in days. Right. So the problem here is we need to propagate, and we're just assuming it's circular, but there is some angular velocity with which it orbits about the sun. So we need something in radians per second. Right. Oh, this does go back to dimensional analysis that we were just talking about in one of the other engineering chats. So we know for a given period, there will be one revolution in the length of that period, so it will travel 2 pi degrees over t days, and then we need to convert that into seconds. So, days are here. We want to get per seconds. That needs to cancel out. In 1 day, they are 86,400 seconds. And so now we can come up with that, right? So in this case, angular velocity of Mercury is going to be 2 times pi divided by 86,400 divided by the period in days, which Wikipedia tells us is 87.9691. All right. What else do we need? We need color. So for Mercury, let's say it's just grayish, right? All right. So we have the code for building a planet now. Let's actually write the internals for the implementation. So basically, it's the same thing we did for the sun, with a few exceptions. So we'll use that as our starting point here. Some radius, right? Some color. We're going to return the resulting mesh. And then we're going to set that position. Oh gosh, there's like a clone or copy from in 3, if I remember correctly. You know what? We're just going to... There are interesting ways you have to worry about copying linear algebra types, depending on what the implementation is. It's different in 3 compared to Sylvester, compared to practically everything else. And then, gosh, are we going to be able to do this? First, let's make sure that works. Oh, we need to stop animating. Stop trying to rotate the sun. Who do you think you are, the Beatles? Okay, so this is where the realistic scale of the solar system starts becoming a problem. If you remember, our z-index issue, or a near-far clipping for the camera was like way out, right? So we didn't have to worry about z-buffers. But as it turns out, that does not help us very much when it comes to seeing like as big as the sun is, right? Like, where is Mercury? Well, it's small and it's really far away, like in a realistic perspective. So there's a couple of things we can do to help here. The first is we're going to tweak this just a little bit to a 60-degree field of view, but we're also going to inflate. So we have an initial position, a radius here. We're going to inflate the radius just a little bit. So we're going to keep the sun normally scaled, but especially for purposes of debugging, say if it's 10 bigger, can we see it? How far away did we say it was? 57 million kilometers. Oh, and it's along the x-axis, so we know where to find it. We know where it should be, right? RGB should be right over here. Two. Oh, 12. Yeah, we'll definitely see it with 12. There it is. There's Mercury. Hello, Mercury. Who's a good little boy? Who's a good little Mercury? Obviously, this starts to give you an appreciation for the problems that come into like astrodynamic scale, right? Hard enough to find as it is. So we're also going to take this initial position and for the time being const spatial multiplied by some scale. Whee. But now we have enough to start, like, okay, that's roughly where Mercury is by some scaling factor, right? So we can go in and start saying, okay, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And go in, and you can imagine these would be coming from a database, right? In our case, our database is Wikipedia. Okay, so radius of Venus is 6051 kilometers. Initial position, again, we'll just offset it by x for now. 108.21 million. Orbital period in days. 2.71. And we'll give it, I don't know, I guess it needs, let's see, grayish yellow would be, I'm entirely guessing. All right, let's see where Venus winds up. Ooh, still too far to see. Hey, there's Venus. Something's wrong. Looks like our radius is crazy. 6.05 E1 E3. There we go. There we go. And we have a relatively consistent scale. I'm going to back this out just a little bit. Let's see. It was 1E minus 1, so 5E minus 2. Have it. Oh. Spatial scale. Oh, that's right. Sorry. 5E minus 1. We're multiplying. All right. We're also going to lighten these colors a little bit, but we're going to do so. Let's see. Let's see. Let's JavaScript do that. So, FF. Okay. That's just an integer value, right? So you can multiply that by something, but it's not going to, multiply individual color values. Wanted to lighten things, so let's increase these values. Can we do 6? Uh, 6. No, we can't. It's gonna interpret that poorly. All right, so we're trying to lighten it here. Since a black background. Okay, there we go. We're not going to worry too much about lighting in this scenario, by the way. Let's do the inner solar system for now. So let's do Earth. There's a few other things I want to be able to add and demonstrate before we add the annotations here. Earth's radius is 6.3781 E3 kilometers. Its neutral position, let's see, 1.495.923 E68. Yeah, that's about right. And then we'll 65 point. If I can remember the right way to round. It's just above a quarter, 256. And then of course we have to make it green, so RGB will go bright, nice bright green. And then Mars for now. Mars is substantially smaller. Mean radius 3389 E3. Initial position, we'll put it out at 227939366 E678. What else we got? Orbital period. 666 days. And of course we have to make it red, right? So let's check it out. See what that looks like. There we go. There we go now. Woohoo! Not bad. Not bad. All right. So, what are we at on time? 40 minutes. Oh man. Kind of hoping to get to a few other things. Let's add some orbit traces first before we do that. So as part of constructing an orbit, in this case we have a scene graph node planet. We're also going to, let's see, let's turn this into structural data. So pretend this data could be coming from a database somewhere. Radius. What did you say that was? That was some major axis. We're pulling that from. I would be doing this in with the units on the end, probably. Orbital period. You know what? Let's do that. Approximate. And let's give it a name. Radius in kilometers, and let's say also in kilometers, or days. Okay, so there's Mercury, Venus, Earth, Mars. I do find this to be a very helpful technique, declaring like static data models within the application you can treat as if they came from somewhere and then swapping them later on. Let's go ahead and add that data now. So major axis, period, color. All right, that's it for Venus. Let's do Earth. You know, we might do a part 2 for this because this stuff is so fun. It's also really useful. There's one point that I want to get to today. Specifically, we'll say orbit traces. And then, I don't know, we'll see how much time we have left for that and how ambitious I feel. I might also just finish it and then walk through it for part 2. All right, there are planets. And now here we can say radius. Did we not change? Yeah, they all have radius. Should know. 3 vector 3 planet. That was semi-major axis. E for type hints. 0, 0. 2 times math pi divided by 6 400 divided by orbital period. And then color, right? Let's see, does that work? Look at that. Everything but color works. So why didn't color work here? Build planet, B color. Approximate color hex. That's my dinner. Boink. Hey, look at that. Okay, so we're going to add some orbit traces. So basically, again, assuming that these are circular orbits, which they're not, they're elliptical, we're going to create a line that goes about the sun. So let's say we have some points we're going to sample, right? Iterate to push. Those points are going to go into a geometry. Set from points using that handy dandy helper. We just need position data, right? And then you create a new 3ds line. We haven't defined a material yet. We'll return that so it gets added. Line basic material. Line materials are, believe it or not, some of the hardest things in computer graphics programming. Let's say we want them to be, I don't know, gray-ish. So now, fun part. Let's have 100 samples. Old-fashioned for loop style. And if I remember correctly, these need to be 3 vectors. So our angle here is going to be 2 times pi times I divided by n. So it will start at 0. Just to make the boundary conditions clear, we're going to go up to n plus 1, and that will close the loop, right? Because that will go to 2 pi instead of 2 pi minus I over n. Okay, so if that's the angle, let's do some trig here. Let's see, x component is going to be r times cosine. We're also going to be a 2-dimensional solar system here. We're going to ignore our inclination of our orbits. There are really interesting ways to actually implement that, but that is enough that we can start doing this. App, scene, add, build, trace, and then ready? Moment of truth. Did it work? Did not work. Why is it not happy? Added the scene, build orbit trace. Did we return it? We return the line. We define the geometry. Did we pass the radius? Oh, sorry, that's the radius of the planet. We need the radius of the orbit. There we go. The main thing missing here is just the fact that we are in, if you look at our axis helper here, our orbit controls assumed that y was up. Z is up in our coordinate frame that we're using here, so we're going to want to change that. Also, this radius does not appear to be lined up with our planets because we're not using the scale. So when we've set a position here, we had a spatial scale. We're going to make that a global parameter. And multiply by that value. And then, gosh, there is a way to do this with 3 orbit controls. See if I can remember what it is. Camera upset. So it's a camera coordinates. That's right, because the orbit controls will use them. Okay. So now if we go in, there we go. Z is up. Orbits online. Check that out. Hey, that's not bad. That's not bad. All right. What are we at? 49 minutes. Now we actually need, you know, the whole point of this exercise is to add the markup, right? So we are going to, we need a way to identify that. We're going to fetch this content first. So this is our sort of on-window load scene instantiation. And then let's see, how do we want this to work? Let's step into design mode here for a second. We have our app, right? There's the sun, and let's say there's Mercury here. We have an orbit trace going around. Let's say there's, I don't know, a window that pops up like dialogue. Sure, a dialogue. Let's say there's a dialogue that pops up when you click on a planet, and that dialogue will have the relevant section of this markup, right? So it will say, you know, you know what, screw it, let's just actually use that markup, right? Let's just move the markup in. So H3, maybe do we need a title? No, it has a title too. So we'll just identify it by this class name here, based on the click. But we do need to be able to detect the click. So this is where things actually get kind of interesting. In 3, and this is a problem unique to any 3D application, by the time the pixels show up on the screen, they've already gone through a fairly hidden pipeline, a set of transforms where the only destination, especially in like WebGL, is the color values of the pixels you see on the screen, right? That's what it's doing, is it's swapping that display buffer out once it aggregates it across each rendering pass. That's just like RGB information, right? So in order to back out the position relative to mouse coordinates that representation showed up as on the screen, you need to do something called ray casting. So if your eyeball is at a point, right, in this 3D space, you can imagine, let's shoot a ray out from your eyeball to some arbitrary place within the scene. That ray will have some sort of distance that can be computed based off of the camera coordinates and all the elements in the scene, in the scene graph, right, all the nodes in the scene graph. That can then be used to determine, given some sort of collision radius, is the distance from that ray to those objects greater than or less than some collision radius. And ray casting in that way is how you can not necessarily worry about backing out or extracting the actual transforms taking place pixel by pixel on the GPU. Instead, do so in a way where you can trigger events within the actual application code at a much higher level. So let's look at how that can be done in 3. We need a raycaster, so we're going to go ahead and construct that. This is a utility class, but it's still global. So we'll say this is part of our app state. This could even be part of the controls if you want to aggregate a controls model. So let's not done. Raycaster. We need to track the location of the mouse, so we figure out where we're casting that ray, right? So we'll need some sort of update function. This is going to update as it's tracking mouse state. We're going to need some representation of that mouse state. That's going to update. And then we're going to need to subscribe that as a user event. We should put this. Okay, so when the pointer moves, mouse position X is going to be our client X minus inner width. We want to transform that into a normalized -1 to +1 space. So that's going to be 0 to 1 there, multiplied by 2 minus 1. Same thing here. All right. And now we have a consistent mouse position that will be updated. In fact, let's go ahead and debug that now, make sure that it's working. Whee! All right, looks good. Technically, since this is a global, right, actually, or it's within the module, so it might not be a global. We might have to set this explicitly. This can make for really nice debugging. So let's do quick search replace here. We will attach everything to the global context window, and now we can inspect those properties anytime we want, right? Hey, look, that's what they are. And despite the fact that this is being built and packed on the fly by V. Hot module replacement. It's a wonderful thing. Now we actually need to do the raycasting, right? So we're going to do this on a draw-by-draw basis. I mentioned those 3 loops earlier, so I'm breaking that rule here. We're going to do this as part of our rendering pass. Here we go. So raycaster, set from camera. Vector 2, window app camera. It's going to update the position relative to the camera transform, frustrum as we call it. And then we're going to have some intersections. Caster intersect objects. What am I? Just gonna look at all the scene children here, and then so we just need it to run periodically, right? Apparently I did mess something up though. Except from camera. Did I just change it too fast? Nope. 3 manual set from camera. Chords undefined. Am I not using this correctly? Let's see. Raycaster. Set from camera. Pointer. Camera. Pointer move. Is it a one-time thing? No, the whole controls are busted. Okay, so yeah, that's definitely an issue. Let's go ahead and say, what do we say? Right. Yeah, chords undefined. So I may have an older reference here in the documentation. Raycaster, we constructed that, right? Did we not construct that? Constructed down here. Raycaster, new 3JS Raycaster. What am I missing here? No, that should be correct. 3 vector 2. Mouse pause. Oh, that's part of the state. Window. App. Mouse pause. Yep. I'll bet that does it. Yep. Ready for this? No collisions. Try this again. There we go. Boink, boink, boink. Okay. So let's have a couple of things here. What are we at? 59 minutes. I really don't want to go on error today. This is a good interim point. So what have we done? We have a solar system, an inner solar system. We have different factories that are helping us out for planets and orbit traces. We have basic raycasting. We have realistic dimensions in our universe with some scaling. Cool beans. That's a great place to stop. You can probably see where a lot of this is going. I'm not sure how much of it I'll stream versus just like work on in my spare time. I didn't expect to do too much on this, but I thought it would be a really interesting demonstration of like development on the fly, especially for like 3D web apps, which is kind of fun stuff. All right, I'll cut it off now that we're an hour 16 seconds. Hope you learned something. I enjoyed doing this. Hope you enjoyed laughing at my mistakes. Take care.